So welcome everybody to this week's problem set number 7. And let me start with a remark in that the problem set of this week and the problem set of next week will be a little bit different than the problem sets that we considered before because so I noticed that after talking with Professor Zurenkova that there is a kind of a delay in the lecture with respect to the topics which are covered, comparing it to the exercise sessions. So I'm a little bit too fast. And therefore, we decided to have two exercise sessions where we are considering kind of exercises from the previous problem sets, so from the previous chapters. Those would be chapters 2 to 6, and yeah, give you some more exercise opportunities. So I decided to make them a little bit more difficult than what we did in the exercise sessions before, just to give you a little bit more practice. So yeah, we started this week with some exercises from chapters 2 to 6, and next week I will pick kind of other exercises from the same chapters, and then in 2 weeks we will continue with chapter number, I think it's chapter number 7 or 8. Okay, so let us start with exercise number 1. Consider a free market with demand equal to Q equal 400 minus 10p and supply equal to 15 times p. So the first question is, what is the value of consumer surplus and what is the value of producer surplus? Good, so we have seen an exercise like this before. So let us aggregate all the information that we have. So we know first that the demand is equal to 400 minus 10p, and that supply is equal to 15 times p. So let us start with sub-exercise A. So in order to find out the equilibrium price, we set equal the demand function and the supply function. If you solve this equality here for P, you end up with an equilibrium price being equal to 16. And if you plug it in either to the demand curve or the supply curve, you end up with the equilibrium quantity, which is then, if you plug it into the supply curve, equal to 15 times 16, and this is equal to 240. And this is everything that we need in order to be able to calculate the consumer surplus and the producer surplus. So the consumer surplus, which I shortcutted here with CR, is equal to the maximum willingness to pay, so the maximum amount of willingness to pay for the product, which is simply found by setting equal to 0 the demand curve. Yeah, so if you want to set equal the demand curve, so if you want to have a price such that the demand curve is equal to 0, you simply set this equation here equal to 0, and if you solve it, you end up with a price equal to 40, and this is the maximum willingness to pay for the product in the market. So for any price above 40, there is no demand in this market because there is no consumer in the market who has a higher willingness to pay for the product than 40. So from 40, we subtract the equilibrium price, 16, because we are now considering all the consumers who have a higher willingness to pay than the equilibrium price, which is equal to 16. To this, we multiply the amount which is traded in equilibrium, so 240, and we divide this by 2. Yeah, so we had an exercise before where we discussed in detail why the consumer rent is looking like this. And if you calculate this, you get a consumer rent equal to 2,880. So let's come to the producer rent. So the producer rent is equal to 16, so the equilibrium price, times the quantity which is traded in equilibrium, 240, divided by 2. If you calculate this, you get 1,920. So those are the consumer rent and the producer rent for this economy. And yeah, we can also calculate the welfare. So the welfare is then simply, total welfare is simply the sum of those two components. So the sum of consumer rent and producer rent, which is then, yeah, if you write it down, so consumer rent plus producer rent. And this is, let me just calculate it 1 second, 4,800. Okay, so basically this is reflecting an amount which tells you how much profit is made in this market, so with respect to the supply side, and how much money do the consumers save relative to their willingness to pay when they're buying the product for the equilibrium price of 16. Okay, so nothing new here basically. I just changed some numbers to give you more exercises. So now comes the new part. So let us go back to the exercise description. So now the government is imposing, so we're at sub exercise B here. So now the government is imposing a tax of X dollars per unit on the consumption of the good. What is the consumer surplus now? This producer surplus. How high is the deadweight loss? How does it change if X is increasing and why? Okay, so before we had a particular, so the exercise before we had a particular amount of the text, which was changed. Here we have a variable. This might make it a little bit more challenging. So the procedure is actually the same. There is just one additional variable that we need to consider. So now the demand function is equal to 400 minus 10 times P plus X, okay, because the consumers are paying on top of the price amount X of taxes. The supply curve does not change. It's still 15 times P. Now, if we set equal demand and supply and solve it for the equilibrium price, we end up with an equilibrium price being equal to 16 minus 2 divided by 5 times X. And if we plug it in to either the supply curve or demand curve, so I will do it again for the supply curve, we end up with 240 minus 6x. Okay, so those are the equilibrium price and the equilibrium quantity in this market, depending on the tax which is imposed on the consumers. So what you might have noticed is that we can actually get the results of the previous sub exercise by simply plugging in x equal to 0 into the expressions here. So yeah, if the government is choosing a tax equal to 0, then obviously the results in this kind of sub exercise will coincide with the results from the previous sub exercise. Yeah, so keep this in mind. Good. So now that we have the price and the equilibrium quantity, we can calculate the consumer rent and the producer rent in when we have taxes. Therefore, to distinguish the consumer rent and producer rent from the previous SAP exercise, I will denote the consumer rent here with the index T for taxes. But yeah, there will be slight changes in the expression because we have a tax now. So we still have a maximum willingness to pay, which is equal to 40 in this market. So this didn't change, but obviously the equilibrium price changed. So from this we subtract 16 and we subtract minus 2 divided by 5 times x. So this is then plus 2 divided by 5 times x. And we multiply to this, the equilibrium quantity, 240 minus 6x, and divide this by 2. And now if you calculate this, you get, use a calculator or some software on your computer to calculate this. Then you get 2,880 minus 24 times x minus 6 divided by 5 times x squared. Okay, so this is the consumer rent with taxes depending on the amount of tax or the height of the tax. So we can do the same for the producer rent. And then we have 16 minus 2 divided by 5 times x. So this is the price, the equilibrium price with taxes, times the quantity in equilibrium with taxes. So 240 minus 6 times x divided by 2. And if you simplify this, you end up with 1920 minus 69 times x plus 6 divided by 5 times x squared. Okay, so this is basically the consumer rent, and so this is the consumer rent and the producer rent if we have a tax equal to x on the consumers. So next, what we can do is we can calculate the dead weight loss, because this was the question in the sub-exercise. So the dead weight loss here can be easily calculated. It's simply the sum. Sorry, let me just check one thing. Okay, so it's the sum or the absolute value of the sum of the consumer rent when we have taxes plus the producer rent when we have taxes minus the consumer rent with no taxes minus the producer rent with no taxes. And I just put absolute values here because the number will be obviously negative, because there will be less total welfare if there are taxes, and hence this absolute value is just making sure that we have a positive term there. And if you plug in all the values and calculate the dead weight loss, what you will get is 120 times x. Yeah, so if you apply the absolute value function on the difference, so the difference will be minus 120 times x, and in absolute terms, this is 120 times x. So this is the dead weight loss depending on the tax which is imposed on the consumers. And as you can see here, the dead weight loss is strictly increasing in the height of the tax. And the reason for this is simply given by the fact that if there are taxes on this market, there will be distortions in that we will have consumers who actually have a higher willingness to pay for the product than the production costs of some of the suppliers. And because of the tax equal to X, the consumer's willingness to pay minus this tax will be lower than the production costs of some of the producers, and therefore trade will not happen between some of the consumers and producers on this market who actually would have traded if there wouldn't have been a tax. Yeah, and this is the reason why we have a dead weight loss. And the higher this tax is, the less will be kind of the willingness to trade for the consumers, because the price, the real price that they have to pay is increasing more and more, and the less efficient the market will be if we are further increasing this X, which is representing the tax on consumers. Yeah, so this is the reason why the dead weight loss is strictly increasing in the height of the tax on consumers. And this finishes exercise number 1. So let's go to the exercise description again. So you have $200 to spend on apples and bananas. The price of an apple, which I denote by capital A, is $4, and the price of a banana, which I denote by capital B, is $10. Suppose that your utility function is given by A by the power of 1/2 times B by the power of 1/2. In sub-exercise A, we are simply asked which combination of A and B we will choose. And yeah, let's start this. So in the exercise, which was similar to this exercise here, we used kind of a substitution approach to solve the optimization problem. just to show you that there is some variety in how one can approach these problems, I will use a Lagrangian approach now. Yeah, so you should be familiar with optimization when you're using a constraint or when you're having a constraint and you're trying to solve this by the Lagrangian approach. So how does the optimization problem in Lagrangian form look like? So we want to maximize our utility with respect to capital A and capital B such that we are fulfilling our budget with equality. So we are maximizing over A, capital A and capital B, and the Lagrangian multiplicator lambda. So we're maximizing the Lagrangian function, which is equal to the utility function. So A by the power of 1/2 times B by the power of 1/2 plus lambda times the income that we have, so 200, minus the price of apples times the amount of apples that we consume, minus the price of bananas times the amount of bananas that we consume. Yeah, so this is the Lagrangian form of the optimization problem, which is given in this exercise here. And you can simply solve this by deriving the partial derivative, deriving the first order conditions with respect to the three parameters here, so the three endogenous parameters, and then you simply solve the optimization problem. So yeah, let us start by taking the partial derivative of the Lagrangian function with respect to the amount of apples. So here, if you take this derivative, you will have 1/2 times A by the power of minus 1/2 times B by the power of 1/2 minus lambda times 4. And this should be equal to 0. And if you rearrange this, what we have is 1/2 times A by the power of minus 1/2 times B by the power of 1/2. And this should be equal to lambda times 4. Yes, I just took lambda times 4 on the other side. Next, so let me go a little bit more on the left here so we have some space. We take the derivative of the Lagrangian function with respect to B. So now we have A by the power of 1/2 times 1/2 times B by the power of minus 1/2 minus lambda times 10. This should be equal to 0. And again, if we rearrange this to bring the second term on the right-hand side, we end up with A by the power of 1/2 times 1/2 times B by the power of minus 1/2. And this should be equal to lambda times 10. So finally, we have the partial derivative with respect to the Lagrangian multiplicator lambda. And this is giving us basically 200 minus 4 times A minus 10 times B. And this should be equal to 0. Yes, so if you remember the substitution the substitution method that we used in one of the previous exercises, what you got there was that you made sure that the constraint is fulfilled by plugging in into the objective function. So you solved the constraint for one of the endogenous variables, and you plugged in this equation for the respective endogenous variable into the utility function, and then you maximize. So by this, you made sure that you're maximizing utility and the constraint is fulfilled. Here, if you're using the Lagrangian approach, this condition here, so the third partial derivative, is making indeed sure that you are maximizing utility and are fulfilling the budget constraint with equality in an explicit way. Okay, so what do we do next? Next what we can do is we need to find out from this, like using this first order conditions, we need to find out the optimal ratio of apples and bananas in equilibrium given the market prices. So by doing so, we simply divide the equations 1 and 2 by each other. So we do this by dividing the left-hand sides of equation 1 and 2 and the right-hand sides. Yeah? So what we do is we divide the left-hand side of equation 1 by the left-hand side of equation 2 and the right-hand side by the right-hand side here. Okay, so then what we get is, if we do this division and simplify, we get B divided by A should be equal to 4 divided by 10. Hence, if you rearrange this, we get the following ratio or relationship. Sorry, there should be a star there. So B is supposed to be 4 divided by 10 times A. So for each unit of A that we are consuming, in optimum, we are supposed to consume 4 divided by 10 units of B, of bananas. So as a next step, what we can do is we can plug in this for the right hand side here for B in the partial derivative number 3, so first order condition number 3. So by doing this, what we get, or let's say plug in 3, so what we get is 200 minus 4 times A minus 10 times, and now we plug in for B, so 4 divided by 10 times A, and this is supposed to be equal to 0. And if you solve this, what you get is A star being equal to 25. So in equilibrium or in optimum, you consume 25 apples. And we can simply plug in this A star here into this relationship here between B and A to get the optimal amount of bananas which are consumed in equilibrium. So then B star is simply equal to 4 divided by 10 times 25, and this is 10. So if we want to maximize utility, given our constraints, we consume 25 units of apples and 10 units of bananas. Now, again, the second sub exercise here is kind of new because now the government is imposing some taxes on apples and bananas, and we are not considering explicit values for or like a particular number for the tax, but we are considering parameters, so variables. And the question here is, suppose the government imposes unit tax of TA on apples and TB on bananas. What combination of A and B will you choose now? What is your indirect utility function? So this is what we will be doing now. So let us consider the optimization problem again now. So we are maximizing over capital A, capital B, and lambda. We're maximizing our Lagrangian function, which is now given by the following. So A by the power of 1/2 plus, sorry, not plus, but it's times B by the power of 1/2 plus lambda times 200 minus 4, and now this is the 4 is the price of apples, but in addition we have to pay TA, an amount TA for each unit of apple that we're consuming. So this times the amount of apples that we consume minus 10 plus TB, so the tax on bananas that we have to pay for each unit of bananas that we consume. Okay, so this is now the new optimization problem that we're considering. So then we go through the partial derivatives again. So we go to the first order conditions. So we start with the partial derivative with respect to A. So this gives us 1/2 times A by the power of minus 1/2 times B by the power of 1/2. This minus lambda times 4 plus TA should be equal to 0. Then the second partial derivative is given by the derivative with respect to B. So then we have A by the power of 1/2 times 1/2 times b by the power of -1/2 minus lambda times 10 plus tb, and this should be equal to 0. And as a third first order condition, we take the partial derivative with respect to the Lagrangian parameter lambda, and this gives us 200 minus 4 plus ta times a minus 10 plus tb times b should be equal to 0. Okay, so I will shortcut a little bit, so I will not now show the step where I'm bringing those terms to the other side of this equation, but yeah, you can do the step for yourself. I would simply go to the step where I'm dividing equation 1 by 2 by dividing each sides of the respective equations to each other. So again, we divide 1 by 2, and what we get then is b divided by a is equal to 4 plus ta divided by 10 plus tb. Okay, so this is the new optimal ratio of consumption if we have taxes given by ta and tb. And if we rearrange this, we get the optimal amount of bananas depending on the amount of apples that we're consuming, just by rearranging this term. Okay, now the procedure is again the same as before. So we plug into equation number 3. And what we then get is 200 minus 4 plus ta times capital A minus 10 plus tb times, now we plug in for this expression here, so we get 4 plus ta divided by 10 plus tb times a, and this should be equal to 0. Now if we solve this for a, we get a star being equal to 100 divided by 4 plus ta. Again, if you set ta equal to 0 here, you end up with 100 divided by 4, which is then equal to 25. So we can somehow check whether we did a correct derivation here by knowing that before, when we had no taxes, we had 25, and now it's also 25 if we set ta equal to 0. So this indicates that we didn't make any mistakes. So if you want to check or get sure that you did something right, this is the way to do it. And then knowing that a star is equal to 100 divided by 4 plus ta, we can plug this into this equation, or the relationship that we derived before up here. So then b star is then simply equal to 4 plus ta divided by 10 plus tb, times 100 divided by 4 plus ta, and this is then equal to 100 divided by 10 plus tb. Okay, so this is giving us the optimal amounts of apples and bananas that we consume if we want to maximize utility, given that we have taxes ta and tb. And the last part of the question was to derive the indirect utility function, and the indirect utility function can be simply found by plugging in the optimal demands for bananas and apples into the utility function. So basically we plug in, so V is denoted, so typically V is denoting the indirect utility function. So it's basically the utility function evaluated at A star and B star, so the optimal demands for the goods, bananas and apples. And if you plug this in, you get, so we write it down here, so A star by the power of 1/2 times B star by the power of 1/2. And if you plug in and simplify a little bit, you get 10,000 divided by 4 plus TA times 10 plus TB. And all of this by the power of 1/2. And the indirect utility function is giving us the maximum utility that we can achieve given taxes TA and TB. And as you can see, it's strictly decreasing in the height of the taxes. Therefore, the indirect utility function of this consumer is strictly increasing in taxes, because obviously, if taxes are increasing, the consumer can consume less of apples and bananas, and hence his utility function will decrease. And this finishes exercise number 2.